Today we're going to be wrapping up the last lecture video for the semester. It is on partial fraction decomposition. This is in particular 10.7. We are not covering 10.8 and 10.8 for this semester because I felt like with the interest of time, it would be more beneficial to have the students study more for chapter 10 rather than making them focus on 10.8, 10.9. Those sections are on systems of inequalities and system or nonlinear systems, which means that, hey, what happens if I have a parabola and a line? How can they intersect each other? Another example is for system of inequality could be, hey, I have these lines. Now with systems of inequality, these lines have to satisfy if it's greater than or less than. So that means we're going to have a shaded area of interest. But we're not going to cover them. You can read that on your own time. We're going to move on to 10.7, partial fraction decomposition. And the key words to look out for this topic is going to be fraction and decomposition. We are going to be decomposing a fraction into multiple parts. So originally, we are comfortable working with, or we should be comfortable by now, working with simplifying or combining two fractions, two rational expressions, such as this. Everybody here should be able to combine these two fractions together, and it should be straightforward. Now, to combine these two fractions, to add them up, we know that we need the least common denominator. Well, what should the least common denominator be when we add these two fractions together? They should be x minus 1 times 2x plus 1. Just get the products. That means to add them together, we need to multiply the first one by 2x plus 1 over 2x plus 1. Doing so, I will have that least common denominator. And I'm going to multiply the second fraction or rational expression by x minus 1 over x minus 1. And then after you multiply them out, you get something like 2x plus 1 plus x minus 1. I'm going to remove the parentheses now, so bear with me. Now I have 2x plus 1 plus x minus 1, x minus 1, and 2x plus 1. And I'm hoping you guys studied a bit for the final exam because that's upcoming, but I'm hoping that no one makes this mistake from the earlier or from the final exam because I saw this in earlier chapters. Do not cancel out the x minus 1 and x minus 1. Do not try to cancel out the 2x plus 1 and the 2x plus 1. We have 4 terms on our numerator. There's addition and subtractions. I cannot. Only if your terms are multiplication. The bottom denominator, has only one term if I treat this as one object and one object. However, I can't do that with the numerator, so there is no cancellation that can happen. However, I can combine like terms for a numerator. If I combine like terms, I get 3x over x minus 1 and 2x plus 1. And then if I'm feeling really brave, I can also expand the denominator. You don't have to expand the denominator. I would actually prefer it if you didn't, but you might also see it as 2x squared minus x minus 1. That's another representation. All right? So this is just review so far. We already know how to add two fractions together or two rational expressions. Now we're going to go backwards. Instead of giving you these two and asking you to add them together, I'm going to give you instead only this rational expression and then ask you, hey, can you decompose it into multiple fractions or multiple rational expressions? And honestly, we are going to use the same knowledge we have from here to this. But there's a few things we need to know. So there are multiple cases when dealing with partial fraction decomposition. Let's go with case 1. If you don't know what cases are, they're pretty much scenarios, situations. You have 4 possible situations. We're only going to cover 3. So case 1 is all about distinct linears for q of x. I use q of x. We didn't even talk about q of x yet. So let's define that. So we have a rational expression, r of x equals p of x over q of x. Now, q of x cannot equal 0. We've already told that story multiple times. I'm not going to rewrite that. Okay? Let this be a rational expression where we have a polynomial over a polynomial. And in particular, and assume or suppose q of x, your denominator can be split up into a factor times a factor times a factor dot 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 times a factor. And these factors are all linear. So let's call them ax plus b, ax plus b, ax plus b, ax plus b. But the key thing is I don't want all of these to be the exact same. So I'm going to denote this as a1, b1, a2, b2, a3, b3, a4, b4. This lets me know that they're not the same. I'm just saying we have distinct linear factors. These are distinct linear factors. The word distinct just means different. They're all different. And linear, you guys should notice by now, means that, hey, my expression has only x to the first power. That's all it means, is x to the first power. Each of these factors have x to the first power and a constant. So we have our distinct linear factors. Now I want to move on to what the theorem actually, or what the case actually is. We have all the setup needed. Now I'm going to let you know that our r of x is just going to be equal to, if I want to decompose it, I will decompose these as multiple fractions added to each other. But in particular, I will have exactly, let's suppose this happens, I don't know, k times, all right? Let's just keep multiplying it k times. So instead of to the fourth, I'm going to erase this. I'm going to put this as k. There are k distinct linear factors. Not 4, there's k. So that means it could be 6, it could be 4, it could be 8, it could be 20. I don't care. Then that means I will have ax plus b, ax plus b, this is the second one, all the way to akx plus bk. And then we have numerators a, b, c, all the way to k. I don't know how large k is, all right? We're just going to keep having our letters. We might run out of letters, I'll be honest, but you know, the idea is that we're just going to have a huge number of linear factors. If we have a huge number of linear factors, that's how many fractions we're going to break it up into. Okay? Now your book uses a sub 1, a sub 2, a sub 3, all the way to a sub k, which is more precise. But I'm going to put down a, b's, all the way to k's, just to give you the intuitive idea. So, what do you notice with this? We notice that our factors are just the denominators. Distinct linear factors. Factors are denominators. How do I know that? Well, let's look at an example real quick. The one that we've already done. This rational expression, this is r of x right here. Okay? Let's assume this is r of x. Q of x is your denominator. Well, if I factor it out, I get this. 3x over x minus 1 times 2x plus 1. If I break it up, it should break up into two fractions, with the first fraction denominator being x minus 1, and the second fraction being the denominator 2x plus 1, or rational expression. Sorry for using the word fraction. It's more so rational expression. And then we look over here. We have x minus 1 as my denominator and 2x plus 1. The only thing that I didn't show you how to get was a numerator. We need to figure that out. So, let's take an example. Let's take the example 5x plus 7 over x cubed plus 2x minus x minus 2. Let's let r of x be equal to this. All right, this is my rational expression. Now, I'll give you guys some time. Factor the denominator. I'll come back in 10 seconds. All right, I didn't feel like waiting for 10 seconds, but if you factored out the denominator, you should have 5x plus 7 all over x squared minus 1 times x plus 2. Now, the problem about this is that this rational expression that we factored it into is not fully factored. We can factor it even more. So let's go ahead and do that. If I factor this out even more, I get 5x plus 7 all over x plus 1, x minus 1, x plus 2. Boom. So now this is what our r of x is. And we can count how many factors I have for my denominator. I have 1, 2, 3. They are all linear because x has an exponent of 1. Each of these has x raised to the first power, which means these are all linear factors and they're all different. So that means I can decompose this into 1 over x plus 1, or sorry, not 1, sorry. Something over x plus 1 plus something over x minus 1 plus something over x plus 2. All right? I do not know my numerators, so I'm just going to choose some letters or placeholders to put for my numerators. Let's use A, B, and C's. You can use, I don't know, E, W, G, F. You can use X, Y, Z. I don't care. Actually, you wouldn't want to use X because we have X already. But just choose some letters. I use A, B, and C's to make things organized. All right? Now, A, B, and C in particular, this is all equal to... Oh, let me write it over here, actually. I like to write it on the left side. This is all equal to 5x plus 7 over x plus 1, x minus 1, x plus 2. All right? I need to figure out what those A, B, and C's are at the moment. But if I add these together, I have to do something with them. In particular, adding fractions or rational expressions together, I need the same denominator. So let's use that idea. I need the same denominator. The first term does not have the least common denominator. A over x plus 1, I need to have the same least common denominator, and the least common denominator will be this guy. So what do I need to multiply this term by to get to the least common denominator? Well, it has an x plus 1, which means all I need to multiply it by is x minus 1 times x plus 2 all over x minus 1, x plus 2. Okay? Now let's look at the b term. What do I need to multiply that by to get to the least common denominator? Well, it has an x minus 1, so I need to multiply by x plus 1 times x plus 2 all over x plus 1 times x plus 2. So far, so good. The c term, I need to multiply that by x plus 1. Oops, let me use a different color. X plus 1 times x minus 1 over x plus 1, x minus 1. So I'm just multiplying all of these to get the same common denominator right now. Okay? I still need to figure out what A, B, and C's are. But this is how I would add the three fractions out together, or three rational expressions. Now, when we have the same least common denominator with three fractions, now when you add those fractions together, all you're actually doing is adding the numerator. So go ahead and write the numerators down. We have A times x minus 1 times x plus 2 plus B times x plus 1, x plus 2 plus C times x minus 1, x plus 1, x minus 1. So I'm just going to add them all up, the numerators. And this numerator should be exactly equal to this numerator, right? If they all have the least common denominator, they should add up to this final numerator. So I get 5x plus 7. Great. How do I solve for A, B, and C now? That is the question we need to answer. Well, even if you don't know how to solve for A, B, and C, everybody here should have an idea of what to do for this problem. If you said FOIL them out, you are right. If you just multiply everything out, you're good to go. So let's multiply everything out. If I multiply all this out, I get a times x squared. And what is that? Plus x minus 2 plus b times x squared. I'm multiplying one by one. I'm not going to multiply all three factors at the moment. I like to do things step by step. Okay? Plus 3x plus 2 plus c times x squared minus 1. All right. This is still all equal to 5x plus 7. Now, I have this. Now I can multiply the last factor. I can distribute all of my my numerators. Remember, a, b, and c are going to be the numerator of your new fractions that you decomposed into. So if I multiply these out, I get ax squared plus ax minus 2a plus bx squared plus 3bx plus 2b plus cx squared minus c is all equal to 5x plus 7. Now, this looks messy. It looks very messy. I want you to simplify it. I want you to somehow make this not look as messy. And instantly, you should think of combining like terms. The problem is, you guys might be confused on how to combine like terms because you guys see A, B, and C's. Well, I'm going to let you know those are constants. They are constants. Treat them as numbers for now. Don't treat them as variables. Treat them as numbers. Yes, they are placeholders, but in particular, those placeholders are fixed. They are frozen. They are set already. They're not going to be numbers that changes. All right, so I need to actually add them together. So let's first look at the first like term we have. I have ax squared. The only like term I have with ax squared is bx squared and cx squared. Those are the only like terms. They all have x squared in common. So, because I'm treating a, b, and c's as numbers, if I wanted to add these three like terms or combine them together, well, that means you add the coefficients. And these are coefficients. So, to add the coefficients, I have to add a plus b plus c. I have to add these guys here. These are the coefficients. If I add them together, their like terms still has x squared when I combine them. Now, the next like term I will have, or ax right here, the next like term I have is positive 3bx, and is there another x term? No, that's it. Which means if I add them together, the 3b is the coefficient of x, and a is the coefficient of x. So I have a plus 3b times x. Remember, your like terms will always have the same variables at the very end. And then the last piece doesn't have an x term on it right here. Negative 2a, 2b, and minus c. Those do not have a single x on it, which means those are our constants. So, I'm sorry. Yeah, I'll do plus. I don't care. Plus negative 2a. What's next? Plus 2b minus c. And this is all equal to 5x plus 7. So I didn't do anything crazy. There's a lot of letters here and whatnot, but nothing I did was out of territory. All I did here, once I have this long expression, all I did was FOIL it out. I expanded it, and then I combined like terms. That's normal. We've always been doing that. We should know how to operate these kind of work so far. So there shouldn't be any confusion. Now, once I combine like terms, I have my form looking like this. This is what happens when I combine like terms. All right, so I combine like terms. We're good to go. Now, with an equal sign, the left side of your equal sign should be equal to the right side of your equal sign. They should be the exact same. But what's wrong? This right side has an x squared. I don't have an x squared here. There is no x squared on the left side. There is none. You don't see it there. So what does that tell you though? If I have an x squared on the right side and not on the left side, they are both equal. They have to both have the same thing. What does that mean? Well, it means that our coefficient here has to be 0 because I don't have an x squared. So what we can say is that a plus b plus c has to be equal to 0. All right, 0 times x squared is 0, and that's why it's gone. Now, look over here. The coefficient of x is 5. The coefficient of x is over here. They're both coefficients of x. They should be the same, which means that now the next equation I can write down is a plus 3b is equal to 5. And then the last part is our constant. This represents our constant. Well, our constant is 7. So that means we have negative 2a plus 2b minus c equals 7. We have a system of equations. Treat the a, b, c as x, y, z if you want to. If you want to solve this system. I'm going to put it in a matrix. You don't have to put it in a matrix. You don't. Sometimes you can solve it by substitution. But if you put it in a matrix, you have 1, 1, 1, 0, 1, 3, 0, 5, negative 2, positive 2, negative 1, 7. This is your matrix. It is a 3 by 4 matrix. You need to find the solution now. So, I'll let you guys know when you're solving these matrices for partial fraction decomposition, you don't have to show work. You do not. As long as you show your matrix right here, the only work required that I want to see is maybe you want to say by graphing calculator. RREF. I've already shown you guys how to do that. Now, if I give you a matrix and I tell you to solve the system, I do expect you to show work, but over here, I'm already testing you on that knowledge. So why make this problem or this topic longer than it needs to be? If I made you solve this system and show all your work, you would have about 2 or 3 pages worth of work. That's too much right now. I will already give you a matrix and ask you to show your work. This one right here, my main goal is if you can split the fractions up. So I don't care about that. So if you put this into your calculator, you get, reduced row echelon form. You're going to get an A value, you're going to get a B value, and you're going to C value. Let's see, did I calculate that? And then if you actually calculate it out, you should get A is equal to 2, B is equal to negative 1, and C is equal to negative 1. Be sure you double check just to be sure. I might not be right, but I want you guys just to make sure that you guys are following along, and if not, then you can show me later on in the email and whatnot. I might have made a mistake. But I got A equals 2, B equals negative 1, C equals negative 1 when I put in my calculator. I might have punched in a number wrong, who knows. But after you got your values, you need to tell me the partial fraction decomposition. So we can say R of x, the original function was 5x plus 7 all over x cubed plus 2x squared minus x minus 2. And if you were confused on how we factored it out, we factored via grouping. Yeah, we factored via grouping. If we have this, the partial fraction decomposition. Remember, we have 3 factors. So I'm going to have 3 fractions. Boom. Now, I know my 3 fractions are going to have the denominator, what was our denominator? X minus 1? Was x minus 1? Let me see. No, x plus 1, x minus 1, and x plus 2. So x plus 1, x minus 1, and x plus 2. Now, I need to figure out the numerators. Well, we're going to use this information. These are our numerators. But you need to know which one goes with which. So that means you got to go back to the original problem up here. And where did we put the A, the B, and the C? Wherever you put those, whichever denominators you have, they should match up correctly. It says here the A matches up with the x plus 1, the B matches up with the x minus 1, and the C matches up with x plus 2. So if I go down here, this is A, B, and C. So this is going to be 2 over x plus 1 plus negative 1 over x minus 1, and then plus negative 1 over x plus 2. This is our partial fraction decomposition. I'm going to call it PFD for short. Okay, this is what I expect to see. So this is what happens when we have distinct linear factors. If they're all different linear factors, like here, I can split up into just 3 different factors and solve for the numerators just like that. So that's great. And again, it's helpful if you know how to solve these linear systems by graphing. So make sure you know on final day you bring a graphing calculator to assist you. So that's case 1. Case 2. Case 2 is we're only going to cover 3. Remember that. Repeating linear factors. Repeating linear factors. So we're going to use the idea of, let's say, case 2, I want to say, suppose Q of x has repeating factors. Repeating factors, and let's let those repeating factors be ax plus b times ax plus b. Let's say this happens k times ax plus b. K times. Such that then, or we can also write this as q of x equals ax plus b raised to the k power. That's the same thing. If they're multiplying k times, I can just raise it to the k power. The k could be 3, it could be 4, or whatever. So we have that idea. It's repeating now. Then the partial fraction decomposition is going to be r of x equals p of x over q of x, which this is going to be equal. Now, I want you guys to understand this idea real quick. So let me just write off to the side real quick. You don't really have to write anything down here, but I just want you to understand the idea. So if I had something x plus 4 to cubed, I can break up this fraction multiple ways. I can break it up where, let's see, zoom out. I can't zoom out. Okay. I can break it up where, oops. Let me see. There has to be a better way than this. On my way. I can break it up into, I need more space. Let's do it over here. X plus 3, or 3 cubed. I can break it up into x plus 3 cubed plus x plus 3 squared plus x plus 3 squared. Something over this. So I can split up into 3 fractions where I have cube, squared, squared, because I'm getting the least common denominator. The least common denominator will be x plus 3 cubed for these 3 fractions, or rational expression. Another way I can do this representation, I can have x plus 3 raised to the 3rd power plus something over x plus 3 to the 3rd power plus something over x plus 3 to the 3rd power. So let me just put A, B, and C's to make it more clear. I can have this situation. I can have this situation where I have all of them being cubed. The first one says 2 of them are going to be cubed. The next one says all of them are going to be cubed. I can also have a situation where I have x plus 3 cubed. If I break this up, it can be broken up into x plus 3 cubed plus something over x plus 3 to the first power plus something over x plus 3 to the first power. So it's hard to actually list all these possibilities. Like, to think about it, when I do my partial fraction decomposition, I have to know how I can break it up. Is there going to be an x plus 3 squared? Because that can make up your x plus 3 cubed. Is it going to be an x, all of them beginning, are all your factors or fractions going to have x plus 3 cubed as your denominator? Or are they going to have x plus 3 cubed and the rest being x plus 3 to the first power? If I found the least common denominator for all of these, it would be x plus 3 cubed. So how do I know which one is correct? How do I know how to properly do a partial fraction decomposition? Well, there's a powerful statement in case 2 that we can discover, or we can go explore. That powerful statement for case 2 states that, hey, if it repeats k times, like 3 times, in actuality, all I need to do is have my k fractions let me erase this now. I will have exactly k fractions, but if they're repeating, that just means I have ax plus b, all the way to ax plus b. To list the possibility for the first, second, and third power, those possibilities I showed you, all we need to list is ax plus b to the first power, ax plus b to the second power, and ax plus b all the way to the k power. If I do that, I capture every possibility of my partial fraction decomposition. All of these possibilities here are going to be listed in this possibility. I will capture all of that, and you're going to see why. But in doing so, right here, I will have the numerators, they're just variables. Remember that. They're just variables. So the variables are going to be, we're just going to start from A, B, C, D, E, all the way to K. Okay? So I have this set of partial fraction decomposition. So it's nothing different except our denominator is going to have all of the powers of the repeating factor. So if it repeats 3 times, oops, what just happened? If it repeats 3 times, that means I need the factor raised to the first power, I need the factor raised to the second power, I need the factor raised to the third power. Okay? So let's do an example. And the example I want to do let's do the example r of x equals x squared plus 1 all over x times x minus 1 cubed. So I already factored the denominator for you. Now, with this rational expression or rational function, we have, 4 factors. There's 3 x minus 1s, and there's a single x as a factor. Which means, if we wanted to break this up, if I wanted to do partial fraction decomposition, I should have exactly 4 different fractions. The first fraction is going to have, or the first rational expression is going to have the denominator x, because that's a factor, right? The second one will have x minus 1. The third one will have x minus 1 squared. Remember, we need to capture every power. If it's x minus 1 cubed, I need to capture x minus 1 squared, and x minus 1 cubed. All right? And let's just choose some variables, a, b, and c, and d. So we're increasing the values. It's fine, though. Now, let's go back to how we add these fractions together, or rational expression. How do we add them? We actually have to get the least common denominator, which means we need to multiply each term to get to the least common denominator. The first term has an x. Boom. Has an x. All it needs is to multiply it by x minus 1 cubed over x minus 1 cubed. Now, some of you guys might have thought that you have to multiply it by x minus 1 cubed, x minus 1 squared, and x minus 1. You can do that. However, you are not getting the least common denominator. You are just getting the common denominator. I want the least common denominator. If you do not get the least common denominator, you will still get the same answer, but you will have a lot of work. You might get x to the 7th once you multiply it, and then they have to cancel out. So that means you have to know how to factor something to the 7th power, which is ridiculous. So try to get the least common denominator. Now B has an x minus 1. So it's missing an x, that's why I need to multiply it by, but it's also missing an x minus 1 and an x minus 1. So I need to multiply this by x minus 1 squared. If I multiply x minus 1 times x minus 1 squared, I will get exactly this denominator. That's key. The third fraction, or the third rational expression, I can multiply c by x times x minus 1 over x times x minus 1. That's hard to see, but you can always just rewind it back and hear the audio. And the last one has an x minus 1 cube as my denominator. Well, I already have the x minus 1 cube. All I need to multiply it by x. Boom. So now, once we have the least common denominators, I can add the numerators together, and they should be equal to the other numerator. So I get x squared plus 1 equals a times x minus 1 cubed plus b times x minus 1 squared plus c times x minus 1 plus d times x. I'm going to erase this now. I don't need that here. Boom. So I have my polynomial. I have my expression. Now, I need to FOIL everything out. Now, if you struggle with FOILing things out, I'm going to let you know you need to multiply one factor by one factor first. Don't try to do all three at once. What do I mean by that? This guy is the same thing as saying a times x minus 1 times x minus 1 times x minus 1. You cannot, or what students like to do is distribute a 3. You cannot do that. You have to FOIL these out. And I'm going to do it step by step. First, I'm going to multiply these two. If I multiply these two, I get x squared minus 2x plus 1. And this is times x minus 1 times a. This is exactly that piece. All right? Now I have to FOIL it again. So if I FOIL it again, I get x cubed minus 2x squared plus x minus x squared minus 2 or plus 2x and then minus 1 times a. Boom. And then this is going to turn out into a times x cubed and then minus 3x squared plus 3x minus 1. Which means if I were to multiply all of this together for the a term, I have ax cubed minus 3ax squared plus 3a minus a. And then now I can multiply this piece out. If I were to multiply the b term out, I'd have x squared. I'm going to multiply this first, FOIL this out. So, or actually, first I have to FOIL, sorry about that. I have to FOIL this piece first. So I have x times x squared minus 2x plus 1, which is going to give me x cubed minus 2x squared plus x. And then lastly, I have plus bx cubed minus 2bx squared plus bx. Yes, this is a lot of record keeping, so make sure you're keeping track of all this. Plus cx. Can I move this? Let me see. I have to move this real quick. I think I can use the lasso tool. Oh, what just happened? Let's use the lasso tool correctly. So if I remember how to use it, boom, 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 boom. Drawing a huge circle here. And we'll just move it to the left a bit. Ah, messed up. Oh well. Plus, what was it? Cx. Plus Cx. And then if I multiply this last piece right here, oh, plus Cx is plus Cx squared minus Cx. You can do the calculations just to be sure, plus dx. So I have all of my terms, and this all should be equal to the numerator of my final one, which is x squared plus 1. All right, now we got to combine like terms. This is a mess, so let's actually, trim it down. Ax cubed, what has x cubed with it? Well, it's positive bx cubed, and that is the only x cubed pieces. So we have the first equation saying a plus b. If I combine like terms, I'm adding the coefficients, times x cubed. Oh, I'm sorry. Yeah, I have that. Let me rewrite that out. I'm just combining like terms. A plus b times x cubed. And then if I go for the next one, the x squared terms, this has x squared, this has x squared, and that's it. So the next term is going to be plus negative 3a minus 2b plus c all times x squared. I'm just adding like terms. And then now I go with the single x's. This guy, this guy, this guy. So now this is going to be plus b or minus c now. B minus c plus d all times x. And then the final constant, your constant is going to be, I'm going to write down here, plus, what is that? So there was a small mistake, but it didn't mess up our problem. This should have been an AX right there. We already covered that, but it's perfectly fine now. See, boom, boom, boom. So I should have had this right here. Fix this up. This should have been 3a plus b, or yeah, plus b. And then the last component is going to be your constant. This is the constant right here. So it's plus negative a. That's our only constant. And this is all equal to x squared plus 1. Now notice on the left side, I do not have an x cubed term, which means my coefficient from an x cubed has to be 0. So my first equation that I get out of this is going to be a plus b equals 0. That's my first one. Actually, I need to make some spaces so you guys can see this clearly. A plus b equals 0. The second equation, right here, do I have an x squared term? Yes, I do. What's the coefficient? The coefficient is 1. If you don't see it, it's a coefficient of 1. So that means I have negative 3a minus 2b plus c is equal to 1. Now, do I have an x term over here? No, I do not. So that means this has to be equal to 0. So I have 3a plus b minus c plus d is equal to 0. This is a d. And then the last one right here, our constant is negative a. Over here, it should be 1. So that means negative a is equal to 1. I have my system of equation. So you can do this multiple ways. You can solve the system by turning it into a matrix and putting in your calculator. Or, if you put in your calculator beforehand, you would get the matrix 1, 1, 0, 0, 0, negative 3, negative 2, 1, 0, or 0, 1, 3, 1, negative 1, 1, 0, and negative 1, 0. This is your matrix you need to put in your calculator and put the reduced row echelon form, RREF. And the last column will tell you all of the solutions. But make sure you read the matrix correctly, just in case. But if you don't want to do it by the matrix, you'll notice that sometimes your system is easy to solve already. If you look at that last row, we can already tell what A has to be. Negative A is equal to 1. That means A is equal to negative 1. Using that information and using the top one, negative 1 plus what gives me 0? Well, that's B equals positive 1. And then for the C's and the D's, that might require some work right there. Might require some work. But let's see. We can solve for C. C is equal to, let's see, positive 3 minus 2, so that's 1. So C is 0, and D is, let's solve for D now. Let's see, negative 1, so that's negative 3. That's plus 1, which is negative 2. Negative 2, so that's positive 2. Boom. We have these values for our numerator. If I use these values for my numerator, let's go back to the original problem, my fractions. Which ones match up with which? So we have x, x minus 1, x minus 1 squared, x minus 1 cubed. I suggest you write this in order so you don't forget and lose track. So my fraction, the partial fraction decomposition, is going to be negative 1 over x plus 1 over x minus 1 plus 0 over x minus 1 squared plus 2 over x minus 1 cubed. Which, if I simplify this, this is going to be negative 1 over x plus 1 over x minus 1. Now, 0 divided by any number is 0. So this is just 2 over x minus 1 cubed. This is our partial fraction decomposition if I have repeated linear factors. Now, notice that earlier I stated that we cover all the possibilities if I list all of the powers. But we don't have an x squared or x minus 1 squared. That means when I did my composition, that wasn't a possibility. However, if it's not a possibility, all that happens is we're going to have a numerator of 0. This is the reason why listing each of the powers as your denominator, x minus 1 squared, and x minus 1 cubed, will give you each possibility. So we're able to find the partial fraction decomposition regardless if our decomposition is supposed to have x minus 1 squared, if it's supposed to have x minus 1, if it's supposed to have x minus 1 cubed. We can cover all of that just by listing those out. So that's case 2. We got one last case to talk about. The last case. The last case will be case 3. And this one is called irreducible quadratics. This time, suppose q of x is equal to some factor ax squared plus bx plus c times some other factors all right? Let's suppose I fully factor it out and I have something like this. One of them is a quadratic, but where ax squared plus bx plus c is not factorable it's not factorable / reducible. It is not reducible. So that means, an example, x squared plus 9. This right here is not factorable. Now, if you do the complete factorization theorem, you can have a factor, but notice that it's imaginary. You have an imaginary factor or imaginary solution / x-intercept / roots. It's going to be x plus and minus 3i. So you have x plus 3i or x times x minus 3i. But I don't want to work with imaginary numbers. So if you have this case right here, then let's see, where's that? then if you have this case, then we can write r of x, which is equal to p of x over q of x. We can write it as, I don't know what these factors are, but I can write it as ax squared plus bx plus c. And then now, I want you guys to go back to what we did earlier over here. In these ones, in these linear factors, notice that my linear factors, it's linear because it has exponent of 1 for my denominators, but my numerators were constants. Now, I want you to think, linear has exponent of 1 for my x value. For the numerator, because it's a constant, what is the exponent of my constant? Does it have a variable attached to it? No. That means that if I have a linear factor and it's to constant, I am going down an exponent because I have x to the 0 power. So for instance, if I look at my solution here, where's that? Right here. These are all linear, x to the first power, x to the first power, x to the first power, x to the first power. All right? And then my numerator is technically negative 1 raised to the x to the 0 power, 1x to the 0 power. All of these have x to the 0 power because x to the 0 power is 1, and 1 times any number is itself. So these are all x to the 0th power for the numerator. I'm going down an exponent. So if I have a quadratic factor or a quadratic denominator, my numerator has to go down in 1 power. Quadratic's power is 2. So I'm going down 1 power, which means the numerator is going to be linear. But there's more details to it because I can have a variable for whatever's times my x. So we're going to call that a. I can also have a variable for a constant. And I don't know how much other factors you have. But for the quadratic portion, you will have a linear numerator. The reason why you have a linear numerator is because you're going down an exponent. Now, we use ax plus b because linear expressions have a constant and they have x to the first power. Okay? Technically, this is x to the 0 power. So we have to have each power. So that's the idea. So, with that in mind, now we can work with the problem. Let's let the example. Let's do 2x squared minus x plus 4 all over, this is a 4, all over x cubed plus 4x. If I wanted to factor the denominator, then you'll notice that you have a GCF. So you can turn this into 2x squared minus x plus 4 all over x times x squared plus 4. Notice this is irreducible. You cannot break that up. X squared plus 4 cannot be broken up without going into the imaginary components or a complex world. So that means I have to use case 3. So case 3 says that, hey, I am going to split this into the number of factors. How many factors do I have in total? I have 1, 2. 2 factors. All right, the first factor is going to have x. The second factor is going to have x plus 4. Those are my denominators. Now, the numerators, we got to figure it out. Well, the first numerator, we don't know what it is, so let's just call it a. All right, let's just call it a. The second one, it has to be a linear fashion, so go ahead and put the x. But you need to put your variables down. So after a, I like to use b, of course. And then you have to have a constant c for a linear. It could have, the constant could be 0. That just means c equals 0. All right, if you don't have a constant, c is equal to 0. That's the idea. But we're just putting that there just in case we do have a constant on our linear numerator. So I have this form now. Boom. And this is all equal to, what was the numerator again? 2x squared minus x plus 4. Let me write this better. This is kind of sloppy. So I have 2x squared minus x plus 4 equals 4. Now, how do you add these fractions together? I'm going to put parentheses there telling you that bx plus c comes together. But how do you add these fractions together, you got to get this common denominator, least common denominator. I'm going to multiply this. This has an x already. So I'm going to multiply it by x squared plus 4 over x squared plus 4. The second one is missing an x, so I'm going to multiply this by x over x. Now, when I set up my system, or when I set up my equation, because I'm adding my numerators together, once they have the least common denominator, I can add the numerators together. And the numerators better add up to 2x squared minus x plus 4. It's equal to a times x squared plus 4 plus bx plus c times x. Now I have to FOIL / distribute it out. So the first one's going to be ax squared plus 4a. That's easy to do. Just distribute. The second one is also easy as well because I have to distribute it. Now I have to distribute it backwards. So some of you guys might be confused on that, but distributing works left side and right side. This just looks different. So now I have plus bx squared plus cx. Now I combine like terms. What are my like terms? Well, x squared, x squared. Well, then I have, if I combine like terms, I'm adding the coefficients. So now this is a plus b times x squared. Now, the next one has an x term. This has an x term. But what else has an x term? Nothing. So this is just plus c times x. And then the last part is the constant right here. There's no x term here, so this is just 4a. I like to use parentheses to let me know what's my constant and all that stuff, the coefficients pretty much. This is all equal to 2x squared minus x plus 4. Now, when you do this, on the left side, the coefficient is 2 for the x squared. This is the coefficient of x squared, so that means a plus b is equal to 2. Now, let's look at the single x. The coefficient for that is -1, so already write -1. And you only have c is equal to -1. And then your constant is 4, but we have 4a on the right side, so that means 4a has to be equal to 4. This is your system. Now, you can put it in your calculator as well with the Gaussian, with the matrix. If you want to put in a matrix, you have a plus, or you have, the matrix is 1, 1, 0, 2. There's 3 variables. 0, 0, 1, -1, and 4, 0, 0, 4. You can put that in your calculator if you would like to. Now, you can look at this one instantly and figure out what the solutions are actually, because down here at the last row we have a is equal to, well, divide both sides by 4, we get a is equal to 1. Now, c, a plus b equals 2. Oh, I'm sorry, this is b. What am I doing? B is also equal to 1, because 1 plus 1 is 2. And then they already tell us what c is. So you don't even need to do it in your calculator. This is why I say that, you can just put it in your calculator for these problems, for the matrix, and then just say by reduced row echelon form or something like that. So these are my solutions to the system. Now I go back to the original fractions. I know r of x has to be, r of x originally was 2x squared minus x plus 4 over x cubed plus 4x. I'm going to break this guy down. The partial fraction decomposition is going to be exactly 1, 2, 3. Oh, I'm sorry. I think it's only 2. Yeah, it's only 2. I'm sorry about that. It's only 2 fractions. The denominator of the first one was x, and the denominator of the second one was x squared plus 4. And now my numerators for these, the first one's going to be 1. The second one is written in terms of bx plus c. bx plus c. So it's going to be the b value, which is 1, x plus c, which is -1. So this is exactly 1 over x plus x minus 1 over x squared plus 4. This is our partial fraction decomposition for case 3. We're able to do irreducible quadratics. Now, we are not going to talk about repeating quadratics or repeating irreducible quadratics, but we can work with repeating linear factors, distinct linear factors, and distinct irreducible quadratics. So we should be good to go. the last thing I'll leave off with is, hey, what happens if I have, I don't know, I'm going to make something up real quick. Let's say I have x plus 2, x minus 2. Let's say I have something like this, right? But then this is A, this is B. What happens if A is equal to 1/3 and B is equal to 1/3? What happens if I have a fraction or decimal as my numerator? This should take you back all the way to chapter 1 or 2. This is just a little remark, by the way. I just want to make sure you guys don't make this mistake. So if I put that in my numerator, this is not simplified. You need to simplify this for me. All right? Don't try to do this in your head or anything. Actually calculate it out. This is 1/3 divided by x plus 2. Divided by x plus 2. Which means if you write it out, this is the same thing as saying 1/3 divided by x plus 2. I'm dividing with a fraction, which means they both need to be fractions. So put a 1 under this. And then if you remember, you keep change flip. 1/3 times 1 over x plus 2. So that means your simplified version should be 1 over 3 times x plus 2 plus, and let's say this is negative. Let's just suppose this was negative right here, just to give you an idea. Negative 1 over 3x minus 2. If I do keep change flip. Boom. Or multiply by its reciprocal, is like what I like to say. So this would be the simplified version right here. Or you can rewrite this as 1 over 3x plus 2 minus 1 over 3x minus 2. If you don't like dealing with the negatives, you can just turn the addition to subtraction. We've talked about that. I like it as addition, but sometimes you might see it in this second form right here. So that's giving you a heads up. That's what happens if you have a fraction as a numerator. This is old material, but I'm just making sure you guys don't make that mistake. So case 1, case 2, case 3, they're not necessarily new material, but with the fraction numerator, it could be. So this is how you do the partial fraction decomposition for these problems. I'll leave it at that. That's the last lecture video. I hope you guys have a good time, good day and whatnot. Make sure you study for your final exam. Make sure you study for the chapter 10 test that's upcoming. And I'm hoping that you guys do the discussion board. That way I can offer feedback on any confusion for these problems. So go ahead and try this chapter 10 part of the final exam review to study for the chapter 10 test. I will catch you guys later. Take care. Bye.